Okay, so the de Broglie's prediction for kinetic energy for electrons with a kinetic energy of 54 electron volts, okay, and rest energy of 0.511 mega electron volts. Um, Using the de Broglie hypothesis, we would predict that the electrons at that kinetic energy have a wavelength of 1.67 angstroms, which again agrees very well with what Davison and Germer measured, or what the Bragg formula predicts for m equals 1. Okay, so for m equals 1, these two, de Broglie's prediction and Davison Germer's results match up very well. Okay, and so that's pretty good agreement actually for these de Broglie's hypothesis and Davison Germer's experiment only were done a few years apart, I think 2 or 3 years apart, and so that's actually pretty good. But the other thing that Davison and Germer did was that they actually checked that that this relationship would hold true for m equals 2, m equals 3, m equals 4. So how can we check that? Well, we know that if we increase the kinetic energy by increasing the accelerating potential, the accelerating voltage, then we should decrease lambda, okay? And if we have, for example, a wavelength which is 1/2 of 1.67 angstroms, okay, then we should still get a peak at this angle for m equals 1, for m equals 2, I'm sorry, and so forth. So if we keep increasing the kinetic energy, we should see, and by increasing the accelerating voltage, there should see a series of peaks of increased scattering intensity at an angle of 50 degrees. Okay, and so again, the Bragg peak should appear at multiples of square root of v, and this is exactly what happened. Here's a plot of the accelerating voltage, okay, and the intensity of the scattered electrons is a function of that accelerating potential, accelerating voltage. And here is the m equals 1 peak, okay, which corresponds to 54 volts. Here is the m equals 2 peak, which corresponds to 4 times 54 volts, so that the square root of that is equal to 2 times, so that the square root is twice what it was at 54 volts. And here's the m equals 3 peak, which is again 9 times 54 volts, so that the square root is 3. Okay, is 3 times the square root of the voltage at 54 volts. So square root of 54 is something like 7 and a little bit. So twice that should be 14 and something. 3 times that should be 22 or so. All right, and so that's what we see. And we also see these peaks that are in between. Okay, this one, this one, this one. And I'll leave it as a homework problem for you to sort of explain those peaks. All right, so that's really the end of this lecture. What we've done is we've gone over the Davison-Germer experiment, which is the first experiment to directly show that electrons have wave-like properties. In order to explain this, we had to use the Bragg. We had to use the Bragg formalism for scattering of waves off periodic arrays, that is crystals. Okay, and putting those two things, putting the Davison-Germer, explaining the Davison-Germer observations using the Bragg, scattering formalism, we're able to show that indeed electrons have wave-like properties, and their wavelengths are as predicted by the de Broglie hypothesis.